Let's practice multiplying complex numbers. Find the result of I and 5i. So let's begin by multiplying the two terms. We have I multiplied by 5i. Let's use the commutative property to rearrange this expression. We have 5i times I, which is equivalent to 5i squared. Let's simplify this by substituting I squared is equal to a negative 1. So we have 5 times a negative 1, which is equal to a negative 5. Example 2. Find the result of the complex number 7 plus 2i multiplied by the complex number 4 plus 3i. So let's write down our expression of 7 plus 2i multiplied by 4 plus 3i. Let's use the distributive property. So 7 multiplied by 4 plus 7 multiplied by 3i plus 2i multiplied by 4 plus 2i multiplied by 3i. Simplifying the expression, we have 7 multiplied by 4 is 28, plus 21i, plus 8i, plus 6i squared. Let's simplify this further by combining like terms. So we have 28 plus 29i plus 6i squared. Let's simplify this even further by substituting the fact that we know I squared is equal to a negative 1 in for the last term there. So we have 28 plus 29i plus 6 times a negative 1, which is 28 plus 29i minus 6. Let's combine our like terms, which is 28 minus 6 plus 29i. So our final complex number is 22 plus 29i. Next, let's review the difference of squares. The difference of squares is a squared minus b squared, or let's say 5 squared minus 3 squared, or x squared minus 3 squared. The difference of squares would be the result of x plus 3 multiplied by x minus 3. This is true because our middle terms will drop out. Let's try this. X times x is x squared. X times a negative 3 is a negative 3x. X times 3 is 3x. And times a negative 3 is a negative 9. Combining our middle terms, we get x squared minus 9, which is equivalent to the difference of squares. Let's try another one. What if we had a squared minus b squared? Well, that's the product of a plus b multiplied by a minus b. Let's go ahead and distribute. So we'd have a times a, which is a squared, a times a negative b, which is a negative ab, b times a, which is a positive ab, and b times a negative b, which is a negative b squared. Simplifying this expression, our two middle terms cancel each other out, and we're left with a squared minus b squared. Let's try one more. 9x squared minus 25y squared. Let's break this up into 3x plus 5y multiplied by 3x minus 5y. Let's distribute our 3x to our 3x to get 9x squared. distribute our 3x to our negative 5y to get a negative 15xy. Let's distribute our positive 5y to our 3x to get a positive 15xy. And let's distribute our 5y to our negative 5y to get a negative 25y squared. Our two middle terms will cancel one another out. We are left with 9x squared minus 25y squared. Example 3. Find the complex conjugate of 5 minus I. Use multiplication to verify your answer. First, let's introduce what a complex conjugate is. The complex conjugate of 3 minus 2i would be 3 plus 2i. The complex conjugate of a real number 8 and an imaginary number of 6i would be 8 plus 6i. The complex conjugate of 10 plus 3i would be 10 minus 3i. The complex conjugate is a complex number that when multiplied by another complex number produces a value that is wholly real. So let's try out our example. If we have 5 minus I, the complex conjugate is equal to 5 plus I. Now let's use multiplication to see if it makes the product of these two complex numbers wholly real. Let's distribute the 5 to the 5. We have 25. Multiply the 5 to the I plus 5i. Distribute the negative I to the 5, negative 5i. And our last two terms, a negative I times I. Simplifying, we have 25. Our two middle terms cancel out. So we have 25 minus I squared. But remember, I squared is equal to a negative 1. So let's substitute that in for our I squared. We have 25 minus a negative 1, which is equal to 26. And yes, this number is wholly real, so it confirms that the complex conjugate of 5 minus I is 5 plus I. Okay, example 4. A parallel circuit has multiple pathways through which current can flow. The following diagram of a circuit contains two elements, 1 and 2, in parallel. The impedance Z of an element can be represented using the complex number R plus Xi, where R is the element's resistance and X is the element's reactance. Both are measured in ohms. If two elements are in a circuit in parallel, the total impedance is the sum of the reciprocals of each impedance. If the impedance of element 1 is Z1 and the impedance of element 2 is Z2, the total impedance of the two elements in parallel is 1 over Z1 plus 1 over Z2. Element 1 has a resistance of 10 ohms and a reactance of 3 ohms. Element 2 has a resistance of 15 ohms and a reactance of 2 ohms. What is the total impedance of the circuit? Leave your answer as a fraction. Let's begin this problem by writing out the impedance for element 1. So we'd have Z1 is equal to a resistance of 10 ohms plus an impedance of 3 ohms. So our complex number for Z1 is 10 plus 3i. Our impedance for element 2, the real part, which is the resistance, is equal to 15 ohms plus the imaginary part of a reactance of 2 ohms. So Z2, our complex number, is equivalent to 15 plus 2I. Now the problem states that the total impedance is the sum of 1 over Z1 plus 1 over Z2. So let's go ahead and substitute in our values. We have 1 over 10 plus 3I plus 1 over 15 plus 2I. We need a common denominator in order to add these two together. We need to multiply our first value in the numerator by 15 plus 2I over 15 plus 2I, multiplying that by 1 over 10 plus 3I. Our second value, we need to multiply top and bottom by 10 plus 3I. Okay, leaving our numerator as 15 plus 2I, let's go ahead and distribute our bottom. So we have 15 times 10, which is 150, plus 45I, plus 2I times 10, which is 20I, plus 2I times 3I, which is 6I squared. Let's take a look at our second value here. We have 10 plus 3I in our numerator, and our denominator, let's go ahead and distribute 10 to the 15, which is 150. Distribute 10 to the 2I, which is 20I. Distribute 3I to the 15, which is 45I. And distribute the 3 to the 2I, which is a positive 6I squared. So let's simplify this by combining our like terms in our denominator. So we have 15 plus 2I over 150 plus 65I plus 6I squared. Adding that to our second value of 10 plus 3I, simplifying our denominator, we have 150 plus 65I plus 6I squared. So we can combine our numerators now that we have a common denominator. So our numerator becomes 15 plus 2I plus 10 plus 3I. Our denominator is 150 plus 65I and plus 6, but I'm going to substitute in a negative 1 in here for I squared. Combining our like terms in our numerator, we have 25 for our real part plus 5I for our imaginary part over 150. Let's combine 150 and a negative 6 to have 144 plus 65I. Our total impedance, Z total, is equivalent to 25 plus 5I over 144 plus 65I.